Returning to one of our first examples, consider the canoe crossing the river. The canoe's arrow is 1.3 meters per second pointed west to east. It is entirely in the horizontal real plane in the positive direction and can be expressed using rectangular format as 1.3 plus j times 0. Or, if you wish to ditch the superfluous multiplication by 0, 1.3. The river's arrow is 0.5 meters per second pointing north to south. It's entirely in the vertical imaginary plane pointed in the negative direction and can be expressed as 0 minus j times 0.5. Or, if you wish to ditch the superfluous addition of 0, minus j.5. Thus far, they should be making sense. When performing complex number addition using complex numbers expressed using solely rectangular coordinates, one simply adds or subtracts the real components with only the real components, and adds or subtracts the imaginary components with only the imaginary components. Don't make this hard. Real with real, imaginary with imaginary. When we add 1.3 plus j times 0 with 0 minus j times 0.5, we get 1.3 minus j times 0.5. The result is another rectangular complex number with a real component of 1.3 and an imaginary component of negative 0.5, as one might expect. Too easy. Because complex numbers are a little different than normal numerical quantities, they're often written differently. Often textbooks write vectors using a script or bold notation, but I find this technique cumbersome and ugly. I find an easier way to annotate a complex number, vector, or phasor is to simply use an overbar. For example, the canoe's complex number in rectangular format could be represented as a overbar equals 1.3 plus j times 0, or just 1.3. The river's complex number in rectangular format could be represented as b overbar equals 0 minus j.5, or just as negative j.5. And finally, the resultant travel vector, a plus b, could be represented as c overbar equals 1.3 minus j times 0.5 using rectangular format. As another example of complex numbers and complex number addition using rectangular format, consider complex number a and b. We're being asked to add a and b. Note both our arguments include real and imaginary components. A has a value of 5 plus j2. This places us positive 5 units horizontally and positive j2 units vertically in the first quadrant. B has a value of 10 plus j3. This places us positive 10 units horizontally and positive j3 units vertically, also in the first quadrant. Note I'm enclosing each complex number in parentheses when I start this problem. You'll understand the utility of this in a moment. Real with real, imaginary with imaginary. When we add complex number a and b together, we're displaced positive 5 plus positive 10, or positive 15 units horizontally, and positive j2 plus positive j3, or positive j5 units vertically. The result being complex number c, having a value of 15 plus j5. As a practical example of complex number addition, one could consider complex number a being worker A pushing some object with a given force at kind of an east-northeast angle. Along comes worker B, assisting worker A with a little bit more force at a slightly different east-northeast angle. The result being displacement of the object in 2 dimensions proportional to each dimensional contribution. If you think about complex number addition in this fashion, it makes sense that worker A and worker B pushing an object in their own fashion result in a mixture of the effects. Consider a slightly different permutation of this problem, A minus B. This is where parentheses are important. Distributing the negative sign into the parentheses, we arrive at 5 plus j2 minus 10 minus j3. Now all we got to do is add up the real with the real and the imaginary with the imaginary as previously. We're left with negative 5 minus j times 1. If complex number addition can be likened as a and b acting together, one can think of complex number subtraction as the difference between a and b, where the head of a with respect to b is positioned negative 5 minus j1 away. Can you dig this on every level that I do? Let's put your understanding of complex numbers and complex number addition and subtraction using rectangular format to the test with these example problems. For most scenarios, I've given you a pair of complex numbers in rectangular format, and I'm asking you to both add and subtract the numbers together. In addition to numerically solving for the result in rectangular format, see if you can depict the arguments and result on a diagram. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. For our first example problem, a has a value of 2.9 plus j 4.1. This places us in the first quadrant. B has a value of negative 5 plus j 5.3. This places us in the second quadrant. When we add a and b, keeping the real with the real and the imaginary with the imaginary, we obtain a combined result of negative 2.1 plus j 9.4. If we subtract b from a, we obtain a difference of 7.9 minus j 1.2. The head of a, with respect to b, appears to be 7.9 minus j 1.2 away. For example problem 2, a has a value of negative 0.5 minus j 3.0. This places us in the third quadrant. B has a value of 6.1 minus j 5.9. This places us in the fourth quadrant. When we add a and b, we obtain a combined result of 5.6 minus j 8.9. If we subtract b from a, we obtain a difference of negative 6.6 plus j 2.9. For example problem 3, a has a value of negative 6 plus j 9.1. This places us in the second quadrant. B has a value of negative 4.6 minus j 5.4. This places us in the third quadrant. When we add a and b, we obtain a combined result of negative 10.6 plus j 3.7. If we subtract b from a, we obtain a difference of negative 1.4 plus j 14.5. For example problem 4, a has a value of 5.7 plus j 8.1. This places us in the first quadrant. B has a value of 0.9 minus j 4.7. This places us in the fourth quadrant. When we add a and b together, we obtain a combined result of 6.6 plus j 3.4. If we subtract b from a, we obtain a difference of 4.8 plus j 12.8. For our final problem, we've got three complex numbers, a, b, and c, and we're being asked to add them together. A has a value of 8.2. It's entirely in the real plane and possesses no imaginary components. B has a value of 0.5 plus j 7.0. There's a very, very small real component, but most of it is positive imaginary. C has a value of negative j 7.1. It has no real component, all of which is negative imaginary. When we add a, b, and c together, keeping the real with the real and the imaginary with the imaginary, we obtain a result of 8.7 minus j 0.1. Note the similarly scaled, yet oppositely pointed imaginary contributions of each complex number almost cancel each other out, such that the majority of the result is real. When taking into account direction, as well as magnitude, one can expect this to occur more often than you may initially suspect. We'll examine electrical applications of this equal and opposite phenomenon in future lectures on resonance and power factor correction. Alright, that's about it for this brief introduction to complex numbers using rectangular format. We'll examine another method of formatting complex numbers, polar format, as well as additional means of manipulating complex numbers like multiplication and division, as well as conversion between the formats and use of the scientific calculator in later lectures. In conclusion, this lecture presented complex numbers using rectangular format, which assigns two coordinates, a real horizontal x component plus or minus an imaginary vertical y component times j. Additionally, we learned to add and subtract complex numbers using rectangular format. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.